So far we've looked at straight lines and their equations. So the equation y equals mx plus c, the gradient intercept form, in abstract terms. We haven't related it to anything real yet. So I guess the main idea of this video is to start to relate this y equals mx plus c, this kind of straight line relationship between two variables, say x and y, to something real. Okay, and there's plenty of real world situations and examples that we can apply this to. An algebraic model or algebraic modeling involves using mathematical formulas to represent some real world situation. Okay, they don't have to be straight lines. It could be curves. In fact, some things follow straight line relationships. Some follow curved a curved relationship like a parabola or some sort of a U shape or whatever. What we're interested in though is we're just interested in linear models. In other words, a real life situation that could be modeled using the equation y equals mx plus c to represent that real world situation. Remember, that's one of the purposes of mathematics. Why do we study mathematics? Apart from being good for the mind, of course, beyond that, we could use that to really to represent some real world situation, and we can use that for prediction if we want to look ahead in time and think, well, okay, if given so much time, how much money would we have, for example, if we're earning money at a particular constant rate. It could be used for population growth, for example, or to predict anything really. Okay. Right, so a linear model is used to represent a real-world situation where the formula is of the form y equals mx plus c. In other words, linear, it's a straight line type relationship between the two things we're looking at. Now, the y variable, okay, in y equals mx plus c is what we call the dependent variable, since it depends on the value of x. And the value of x is the independent variable. That means that x, we have full control over that. We could make the pronumeral x whatever we like, I guess within reason, depending on the situation, of course. The y variable has to be calculated from the x variable. In other words, we can't just go and say, oh, we're just going to make y 5. Well, that depends on what value we have to set the x variable to make that the y value 5, for example, depending on whatever it is we're looking at. So y value or the y variable, we don't directly control that. We only control the x, and that in turn changes the y. Now, the dependent variable is shown on the vertical axis. Now, you know that the vertical axis, I'll just do it here. So, right, that's the y-axis, or traditionally the y-axis on the number plane, and the independent variable, okay, is on the horizontal axis, which is traditionally the x-axis. Okay, moving on. We're talking about straight lines. Straight lines have a gradient and a y-intercept. Okay, even if it passes through the origin, all lines, apart from vertical lines, of course, or perfectly vertical lines, will have a gradient and some y-intercept, of course, unless the vertical line itself happens to be the y-axis itself. But we're not going to consider those in this video. They can be found using the gradient formula. We've seen this formula already. So m equals y2 minus y1 over x2 minus x1. y2 minus y1, this is the change in the dependent variable, okay, the vertical axis, over the change in the independent variable, okay, so this is the change horizontally, okay, so vertical change over horizontal change, rise over run. And of course, the y-intercept can be found, and we've seen this already, if we rearrange the formula y equals mx plus c, move the equal sign over, okay, and we turn the equal sign into a minus sign, okay. So basically what we've done is rearrange the formula, the mx, move it over, make it negative, and you leave the c isolated, so it becomes the subject of the formula. Even though the subject should be on the left-hand side, it doesn't really matter in this case, okay. It just makes it easier, I guess, to note and to recall, where necessary. So y minus mx will give you the y-intercept, and therefore we can then come up with the equation of the line that represents whatever situation we're dealing with. So one real-world example of linear modeling is, for example, income earned over time, okay, such as wages. What is a wage? A wage is an hourly rate, okay. So, for example, someone earning $25 per hour, every hour that passes, or every hour that they're at work, $25 is earned. Okay, another hour, another $25 is earned. So it's a sort of a constant rate. Okay, and again, I use that keyword rate, gradient, rate. Basically the same thing. The gradient represents the rate, and it's shown by the steepness of the line. So in this case, and I guess I've already sort of went ahead of myself a little bit there, the gradient would represent the rate of money earned with respect to time. Okay, so here's a situation here dealing with income, wages. The dependent variable would be the money earned. Okay, the independent variable would be time. Okay, I'll just make that a bit clearer there. Yep, that would be the time variable. Notice that I'm not using X and Y. You don't have to. So this could be income, so that could be I, for example. We could use that. And time, we could use the letter T, okay, to represent the independent variable rather than using the letter X. So our equation, instead of being Y equals mx plus C, this would be in the form I is equal to M, so the gradient of the blue line, T plus C, and the C in this case looks like it's passing through the origin, so the C would be 0 in this case, but instead of using Y and X, I'm using I and T. Okay, so whatever variables or whatever the pronumerals we use, the dependent variable is always on its own, and the independent variable is multiplied by the gradient, then added on to the y-intercept. Okay, in the next video, we're going to look at a couple of examples, okay, where we're going to model a couple of real life situations, come up with the equation, and use that to predict or for prediction purposes.